The cosmic dance of Pluto and Neptune, a tale of orbital intrigue. In the vast silent expanse of our solar system, where planets waltz in predictable orbits around the sun, one distant world has long captured the imagination of astronomers and stargazers alike. Pluto, once hailed as the ninth planet, this enigmatic dwarf planet has been thrust back into the spotlight, not for its demotion and status, but for a far more dramatic reason. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku have raised an eye-braising possibility. Could Pluto, the underdog of our cosmic neighborhood, be on a collision course with the mighty Neptune? This speculative scenario, steeped in the complexities of celestial mechanics, invites us to explore the intricate dynamics of orbits, the gravitational tug-of-war between planets, and the potential consequences of a cataclysmic event that could reshape our understanding of the solar system. Is this a cosmic whim, a far-fetched fantasy, or a glimpse into a distant future where chaos reigns? Let's embark on a journey to unravel this celestial mystery. The peculiar path of Pluto. Pluto, discovered in 1930 by astronomer Clyde Tombaugh, has always been an oddity in our solar system. Unlike the 8 major planets, which trace nearly circular paths in a relatively flat plane around the Sun, Pluto follows a wildly eccentric and tilted orbit. Its journey takes a staggering 248 years to complete a single lap around the Sun, meaning that since its discovery, Pluto hasn't even finished one full orbit. This elongated elliptical path swings Pluto as close as 4.4 billion kilometers to the Sun at its nearest point, perihelion, and as far as 7.4 billion kilometers at its farthest, aphelion. For about 20 years of its orbit, Pluto even ventures closer to the Sun than Neptune, defining position as the solar system's outermost known body. What makes Pluto's orbit truly remarkable is its steep inclination. While most planets orbit within a few degrees of the ecliptic plane, the imaginary flat disk that defines the solar system structure, Pluto's orbit is tilted by a dramatic 17 degrees. This gives its path a roller coaster-like quality, weaving above and below the plane of the other planets. But the most intriguing aspect of Pluto's orbit is its intersection with Neptune's. At certain points, their paths appear to cross, raising a natural question: why haven't these two worlds collided? The answer lies in a delicate cosmic choreography governed by gravitational forces and orbital mechanics. The gravitational ballet. Why Pluto and Neptune haven't collided. To understand why Pluto and Neptune have coexisted peacefully for billions of years, we must delve into the intricate dance of celestial mechanics. The solar system is a dynamic system where the gravitational pull of each planet influences the others, creating a complex interplay of forces. For Pluto and Neptune, this interplay is governed by a phenomenon known as a 32 orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance acts like a cosmic metronome, ensuring that when Pluto crosses Neptune's orbital path, the two bodies are never in the same place at the same time. This spatial separation is further reinforced by a concept called asynchronous vibration. When Pluto ventures into Neptune's orbital plane, it is always at least 90 degrees away from Neptune itself, positioned either far ahead or far behind in its orbit. This clever arrangement prevents any close encounters, much like two dancers moving in sync, but never stepping on each other's toes. Additionally, Pluto's orbit experiences orbital precession, a gradual shift in the orientation of its elliptical path. This means that when Pluto is at closest approach to Neptune's orbit, it is often positioned high above or below Neptune's plane, adding another layer of protection against a collision. Another critical factor in this cosmic equation is the so-called VJ wobbling, a term inspired by the work of astronomers who study the gravitational interactions between celestial bodies. This wobbling refers to the subtle perturbations in Pluto's orbit caused by the gravitational influence of Neptune, the Sun, and other giant planets like Jupiter and Saturn. These perturbations create a dynamic equilibrium, ensuring that Pluto's orbit remains stable over vast timescales. Mathematical simulations conducted in the late 1980s revealed that despite its chaotic appearance, Pluto's orbit is remarkably resilient, maintaining its stability for billions of years. The role of the giant planets. Neptune isn't the only player in this cosmic drama. The giant planets Jupiter, Saturn, Uranus, and Neptune exert significant gravitational influence on Pluto, shaping its orbit and ensuring its stability. Jupiter, with its immense mass, plays a particularly crucial role. Its gravitational pull helps anchor Pluto's orbit, preventing it from veering too far off course. Saturn and Uranus contribute as well, creating a symphony of gravitational forces that keep Pluto's erratic path in check. This delicate balance highlights the interconnected nature of our solar system. Without the stabilizing influence of the giant planets, Pluto's orbit could become dangerously unstable, potentially leading to collisions or even ejection from the solar system. The 3:2 resonance with Neptune, combined the gravitational nudging from Jupiter and others, ensures that Pluto remains a well-behaved member of the solar system, at least for now. The chaos of orbits, a glimpse into uncertainty. Despite this apparent stability, Pluto's orbit is not immune to chaos. In the realm of celestial mechanics, chaos refers to the extreme sensitivity of a system to its initial conditions. For Pluto, even a minuscule change in its position or velocity could lead to dramatically different outcomes over time. In the late 1980s, computer simulations revealed that Pluto's orbit exhibits chaotic behavior, meaning that small deviations in its starting conditions could result in vastly different orbital paths after just a few hundred years. Yet paradoxically, this chaos does not spell doom for Pluto. Over billions of years, its orbit remains stable within a certain range thanks to the stabilizing forces of resonance and gravitational interactions. This balance between chaos and order is a hallmark of celestial mechanics, reminding us that the universe is both predictable and unpredictable, governed by rules that are at once rigid and flexible. The alarm bells, Tyson and Kaku's concerns. So why, given this intricate balance, are prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku sound the alarm about a potential Pluto-Neptune collision? To answer this, we must first consider perspectives of these two scientific luminaries. Neil deGrasse Tyson, a household name in popular science, is known for his ability to distill complex cosmic concepts into accessible ideas as a key figure in the decision to reclassify Pluto as a dwarf planet in 2006. Tyson has long been fascinated by Pluto's unique place in the solar system. He views the reclassification not as a demotion, but as a reflection of our evolving understanding of celestial bodies. For Tyson, Pluto's story is one of discovery and adaptation, a testament to the ever-changing nature of science. However, Tyson's recent comments about a possible Pluto-Neptune collision introduce a note of caution. He acknowledges that while the current orbital dynamics keep Pluto and Neptune safely, Michio Kaku, a theoretical physicist known for his explorations of the cosmos, shares Tyson's fascination with the unpredictability of planetary orbits. Kaku's work often delves into broader implications of celestial mechanics, from black holes to distant galaxies. For him, the Pluto-Neptune scenario is a reminder of the inherent instability of complex systems. While the 3:2 resonance and other stabilizing mechanisms have kept Pluto safe thus far, Kaku warns that the solar system is not a static entity. Over vast timescales, gravitational interactions could disrupt this delicate balance, potentially leading to catastrophic consequences. The consequences of a cosmic collision. What would happen if Pluto and Neptune were to collide? The scenario, while speculative, is worth exploring for its potential impact on the solar system. Pluto, with a diameter of about 2,377 kilometers, is a small body compared to Neptune, which spans roughly 49,244 kilometers. A collision between these two would not be a simple crash, but a complex event with far-reaching consequences. If Pluto were to collide with Neptune, the impact would release an enormous amount of energy, equivalent to billions of nuclear bombs. Neptune's thick atmosphere, composed primarily of hydrogen, helium, and methane, would likely absorb much of the impact, but the collision could disrupt its atmospheric dynamics, potentially altering its iconic blue hue or triggering massive storms. Pluto, being far smaller, would likely be obliterated or fragmented into countless pieces. some of which could become new moons or contribute to Neptune's ring system. The debris from such a collision could pose a significant hazard to the solar system. Fragment of Pluto could be flung into new orbits, potentially intersecting with the paths of other planets or moons. While Earth is far too distant to be directly affected, the disruption of Neptune's orbit could have ripple effects, subtly altering the gravitational balance of the outer solar system. Over millions of years, these changes could influence the orbits of other bodies, potentially destabilizing the delicate equilibrium that has persisted for billions of years. Implications for Earth and beyond. The idea of a Pluto-Neptune collision raises broader questions about the stability of our solar system and our place within it. While such an event is unlikely to occur within human timescales, it underscores the dynamic and ever-changing nature of the cosmos. The solar system is not a static museum, but a living, breathing system where planets, moons, and asteroids are in constant motion, influenced by the invisible threads of gravity. For Earth, the immediate consequences of a Pluto-Neptune collision will be negligible given the vast distances involved. However, the event could serve as a wake-up call for humanity to deepen our understanding of celestial mechanics and invest in technologies to monitor and potentially mitigate cosmic threats. Asteroid impacts, for example, are a more immediate concern, and studying the dynamics of distant bodies like Pluto could provide insights into how to deflect or manage such hazards. Beyond practical implications, the Pluto-Neptune scenario captures imagination, reminding us of the mysteries that still lie beyond our reach. Pluto, once a planet and now a dwarf planet, continues to challenge our assumptions about the solar system. Its chaotic orbit, shaped by the gravitational interplay of its neighbors, serves as a microcosm of the universe's complexity, a reminder that even the most seemingly stable systems can harbor the seeds of chaos. The future of Pluto studies, the concerns raised by Tyson and Kaku, highlight the importance of ongoing research into Pluto's orbit and its interactions with the rest of the solar system. Advances in computer simulations, such as those pioneered in the 1980s, continue to refine our understanding of celestial mechanics. Future missions like those proposed to explore the Kuiper Belt, Pluto's cosmic neighborhood, could provide new data on the dwarf planet's environment and its long-term behavior. Telescopes like the James Webb Space Telescope and upcoming observatories will also play a crucial role in monitoring distant objects like Pluto and Neptune. By combining observational data with sophisticated models, astronomers can better predict the future paths of these bodies and assess the likelihood of catastrophic events. These efforts not only deepen our understanding of our solar system, but also shed light on the dynamics of other planetary systems across the galaxy, a cosmic reminder. The story of Pluto and Neptune is more than a tale of orbits and gravitational forces. It is a testament to the beauty and complexity of the universe. Pluto, with its eccentric path and defiant spirit, challenges us to question our assumptions and embrace the unknown. The possibility of collision with Neptune, while remote, serves as a reminder that the cosmos is a place of constant change, where stability and chaos coexist in a delicate balance. As Neil deGrasse Tyson and Michio Kaku remind us, the study of space is a journey of discovery filled with surprises and unanswered questions. By keeping our eyes trained on the stars and our minds open to new possibilities, we can continue to unravel the mysteries of our solar system and beyond. Pluto, the little dwarf planet that could invite us to join this cosmic dance. One step, one orbit, one revelation at a time. Unraveling the three-body problem at the heart of the Pluto-Neptune dynamic lies one of the most perplexing challenges in celestial mechanics: the three-body problem. This mathematical conundrum seeks to predict the motion of three celestial objects, such as Pluto, Neptune, and the Sun, based on their mutual gravitational interactions. Unlike the two-body problem, which can be solved with relative precision, think of the Earth orbiting the Sun. The three-body problem introduces a level complexity that defies exact solutions. The gravitational pull of each body tugs on the others, creating a chaotic dance where even tiny changes in position or velocity can lead to wildly different outcomes over time. For Pluto, the free body problem is particularly relevant because its orbit is influenced not only by Neptune, but also by the Sun and the other giant planets. The VZJ wobbling, named after astronomers who studied these gravitational perturbations, describes how these interactions cause subtle shifts in Pluto's path. These shifts, while small in the short term, can accumulate over millions of years, potentially altering the delicate balance that keeps Pluto and Neptune apart. Computer simulations, which have become indispensable tools for astronomers, allow scientists to model these interactions by tweaking initial conditions and observing how Pluto's orbit evolves. These simulations reveal a fascinating duality. Pluto's orbit is both chaotic and stable, a paradox that underscores a complexity of the solar system. The late 1980s marked a turning point in our understanding of this dynamic. Advanced computational models showed that Pluto's orbit, while sensitive to initial conditions, is stabilized by the 3:2 resonance with Neptune and the gravitational influence of Jupiter and Saturn. These models also highlighted the limits of our predictive power. Even with the most sophisticated simulations, long-term forecasts for chaotic systems like Pluto's orbit are fraught with uncertainty. A slight miscalculation in Pluto's position or velocity could mean the difference between a stable orbit